After you did the mid-band equivalent circuit drawing, so you can proceed with the AC analysis. So there are three important parameters that you need to analyze. First is the input impedance, and then we have the output impedance, we have the gain. So if you consider this amplifier circuit, this is the very general representation of the amplifier circuit. So the input impedance is actually the input voltage over the input current. And then the output impedance is the output voltage over output current with the condition where the supply or the input is equal to 0. Okay. So what you do when you want to measure the output impedance is you need to ground the VS, the input here, need to be grounded, and then you can apply the voltage at the output and measure the current. From that, you can calculate the output impedance. Okay, and then analysis is the gain for the gain. As for the gain, we have many type of gain. Two main gains is voltage gain and current gain. So voltage gain we have different type of voltage gain. So we have what we call it AVOC, we call AVS. So each of them has its own definition. What is AVOC? What is AV? What is AVS? Okay, for the gain, we also have the current gain. Current gain in general has two types, AI and AIS. Okay, so we do the analysis. Okay, first we do the analysis on what we call it common emitter fixed bias configuration. So this is the common fixed bias configuration. So the input is at the base, output is at the collector. The impedance input and output is moderate, which is not too high and not too low. And then the result, the gain, voltage and the current gain of this amplifier circuit is quite high. And another characteristic of this configuration is there will be a phase shift between input and output. So this statement means that if the input is a sine wave, okay, so this is input. When you have the phase shift around 880, so the input is inverted. So it become something like this. So this is the output. Okay, how we can do this? First, if you have the circuit, you need to convert it to the mid-band equivalent circuit. Okay, see here. Let's say we have done it from in the previous video. So let's say we have done it. Okay, so the next step is to calculate the input and output impedance. So the input impedance is ZI. This is ZI here. Is the impedance seen from the input port. So from the input port, you will see RB and RPi. So RB and RPi are connected in parallel. So that's why the ZI is equal to RB parallel with RPi. For the output impedance is seen from the output port. So actually we will see the RC, R0, GM, V pi. But take note that the output impedance we need to consider when the Vs is equal to 0 or when the input impedance is equal to 0. When input impedance becomes 0, we see here V pi also 0, and then there will be no current here. GM V pi is always also become 0. So what remain is R0 and RC. So Z out is equal to RC parallel with R0. If R0 is infinity, so Z out is equal to RC. Okay. Next, we analyze the gain for this fixed bias configuration. So as I mentioned before, there are many types of gain. So for example, we have the AVOC, we have AV, we have AVS. So now we consider the AVOC. So what is AVOC? The OC here is actually refer to the open circuit. So open circuit here is actually at the output port, which means that no load connected. So there's no load connected. So that's why it's called it AVOC. So the VOC is defined by VOOC over VI. Okay. So if when you have the gain here, so you see here is defined by VOC over VI. So what you need to do is you need to derive what is the VOOC, and then you need to derive the equation for VI. So what is VI? After you have these two equations, so you can insert in this equation, you can get this answer. Okay, for example, you know the VOOC here is voltage from this point with respect to the ground. So you know here, this is the current source facing toward downward. So because the voltage here is the polarity positive of the V out is positive, is at the upper point. So the current should be towards this direction, or we call it C as a clockwise direction. So you need to define this current direction. So this current direction is equal to the minus Gm V pi. So the magnitude is similar to the current source, but the polarity or the direction is minus, opposite. Okay, that's why you put is minus. Okay, so the voltage here, the voltage across from this point to this point is can be calculated using the Ohm's law. You can combine the RC and R node. You can combine the RC and R node as one resistor, which is R node parallel with RC, and then the current across this total resistance is minus Gm V pi. So V out OC is equal to, current is minus Gm V pi, the resistor is R node parallel with RC. Okay, so you got, this is the first equation. So and next, what is VI? So VI is from this point as with respect to the ground. So the VI and V pi is in parallel. So V pi is equal to, so VI is equal to V pi. So that's why we got here, this is V pi. Insert in this equation, the V pi can be cancelled out. So lastly, you can get the AVOC is equal to minus Gm R node RC. Okay, if the R node is infinity, so AVOC is equal to minus Gm RC. Okay, if there is load connected to the output, so here the output is not AVOC. Sorry, the output is not VOOC. The output will become we can denote, we can use the symbol of VO or VL. Okay, so VL is voltage across the load, VO or VL. Okay, so here the gain will become AV. AV is V out over VI. Okay, what is V out? What is VI? Okay, as defined by previous slide, VI is equal to V pi. How about V out? V out is the similar approach. The current here is minus Gm V pi. So we combine R node, RC and RL to become one resistance. So the current across this total resistance is minus Gm V pi. So we have, this is minus Gm V pi times R node parallel with RC parallel with RL. So this is the first equation. Second equation, so you combine this one, AV is equal to minus GM V pi R naught parallel with RC parallel with RL. So and then this one is over V pi. So cancel out the V pi. So you got this answer. Okay. So next is another type of voltage gain. We call it AVS. So AVS in this circuit is defined as VL over Vs. So here Vs and Vi are two different parameters. So Vs is the supply voltage, Vi is the input voltage. So Vi is lesser than the Vs. So how we can calculate this one? Okay, so VL we have done the analysis. VL is minus GM V pi times R naught parallel with RC parallel with RL. So how about the Vs? Okay, for Vs, we can start with the, we can use this one. Vi is equal to V pi and then is equal to voltage divider. So voltage divider here, what is the, so this is the voltage divider between the RS and between the amplifier. Okay, so here you need to remember that the what is the resistance that related to the input port, because we are analyzing the voltage drop at the input. So the related impedance or resistance at the input port is Zi. So we will use the Zi to do the voltage division. So V pi is Zi over Zi plus Rs times, so this is Vs. So and then you get here Vs is equal to Zi plus Rs over Zi V pi. So you got, this is the first equation, the second equation. This is the first equation. From this equation, you combine this equation and then you can get this answer. So AVS is minus GM R naught parallel RC parallel with RL times Z in over Z in plus Rs.